Hi, this is Dr. Viv. Let's study some basic properties of matrices in this video. So the first property that you may have learned in elementary courses is matrix multiplication. Now there's a recipe for this, and it only works if you have an m by n matrix multiplying an n by p matrix. So these two have to be the same. Now this might lead you to wonder why those n's have to be the same and if there's some deeper structure to this whole process. And that's what I'm going to try to show you in this video, among other things. So first of all, what I'll do is this. I'll write each of these vectors in the matrix A as a row vector. In other words, I'll make a row vector out of each of these. So there are going to be a total of m row vectors. So I'm going to write the matrix A as follows. Rewrite it as follows. A is equal to V1, where V1 is that entire row, all the way up to Vm. For the matrix B, you can probably guess what I'm going to do. For matrix B, I'm going to club columns into vectors. Let me call these W. Now because there are going to be P of these, I'm going to have to arrange them in a row. Here there were M of these and I had M of those in a single column. Now I'll have a single row. Let me call these vectors W. So I'll have vectors W1, where W1 is equal to that entire column, all the way up to WP. WP. All right, so let's try to understand what A multiplied by B actually is. So when I do A times B, what I'm doing is I'm placing these vectors V1, Vm, and W1, WP. Notice there are M of these vectors and P of those vectors. And in general, M and P do not have to be equal. They can be very different. So we're going to be getting an interesting structure here, and that's called the dot product. So the first row of the result is just V1 dot W1, and I'll keep going like this till I exhaust all the V1s dotted with W's. So there are going to be P such entries. Okay, in other words, you're going to have a column strength of P. Now I play the same game with V2. So I'll write one more row. V2 dot W1 all the way up to V2 dot WP. And then to the last entry, Vm dot W1, Vm dot WP. So each vector is dotted with every other vector. So every single vector sees every other vector in this dot product. V1 sees all of the W's in the first row, V2 sees all of the W's in the second row, and Vm sees all of these vectors in the last row. In this manner, we have actually got our result, which is an m by p. Remember, the n's cancel out, and I'm left with an m by p result, m rows and p columns. So that's a great way to understand what you already probably know from having taken some elementary courses where you learned this just as a recipe, but now this is a deeper understanding of what it is. The general term is going to be vi dot wj, and that's just given by the following: ai1 b1j plus AI2 B2J all the way up to AIN BNJ. Now that's just, we can use the Einstein summation convention if you like, and I can write this as AIK BKJ. So that is a great way to understand how matrices multiply in the Einstein summation notation. If I indicate the product as C, then the general term Cij, which is also equal to Vi vector dot Wj vector, is given also by this symbol Cij, which is AIKBKJ. Remember, by the Einstein summation convention, repeated indices are summed. I and j are not repeated because I occurs just once on the left side and just once on the right side, and same with j, but k is repeated on the right side. So that's one way of indicating the general element of this product. Now the one thing I have to tell you about matrices is that they don't commute, and matrices that commute are very special and will be studied in some detail later when we study group theory. But in general, one property is that in general, AB is not equal to BA. In fact, in some cases, BA may not even exist. For example, if I try to form BA, I'm going to get an n by p matrix multiplying an m by n matrix. Well, that does not even have the p and the m the same, so BA may not even exist. Or one of them may not even exist. So that's one important property of the product, and there are many other important properties. Now, matrices have a rich zoology to them, and we'll study more of the zoology when we talk about group theory. But right now, I just want to talk about some basic matrices. One is, when is a matrix said to be symmetric? Symmetric matrices play a big role because not only are they beautiful, but they are used in physics a lot. So a matrix is called symmetric when the transpose is equal to the matrix itself, which means that if you interchange the rows and the columns, you get back the matrix. A simple example of a symmetric matrix is 1, 2, 2, 1. Now if you interchange the rows and the column, it looks exactly the same. So that's an example of a symmetric matrix. Then you have the concept of a skew-symmetric matrix, or sometimes simply called antisymmetric. A skew-symmetric matrix would be one that has got A transpose equals minus A. Now the characteristic of a skew-symmetric matrix is that the diagonal is always 0. So how about something like that? That does satisfy A transpose. If you bring 0 and 1, which is a let me try to do the transpose of this. So the transpose of this is going to be 0, 1, minus 1, 0. In other words, I made the row the column, the row. So that's the transpose, and you can notice that if I take a minus outside, the minus multiplies all the entries, so that's minus 1, 0, and so that satisfies A transpose equals minus A. And in all this, the diagonal has to always be 0, because the only element whose negative is itself is 0. So matrices are of those two types. What if you have a matrix that does not answer to either of those two types? And there are an infinity of them too. Well, actually it turns out, and I show this in my notes, that any matrix can be written as a sum of symmetric and skew-symmetric. So this is a useful trick to have, and this is how I'll do it. If I take a matrix B, I'll write it as 1/2 B plus B transpose plus 1/2 B minus B transpose. Well, what have I done? I've simply written B as half B plus half B, and then subtracted and added half B transpose, but done it in such a way that this one is actually a symmetric matrix, and that one is actually a skew-symmetric or antisymmetric matrix. So I have written any matrix B, and this matrix is completely general, it doesn't have to have any properties whatsoever, as a sum of symmetric and skew-symmetric matrices. Now this can be done for various other types of matrices later. We'll see that it can be done for orthogonal matrices and Hermitian matrices, unitary. It can be done for all kinds of matrices. So let me just talk about orthogonal next. It's a very important class of matrices called orthogonal matrices, and especially useful in the subject of rotation groups. Now, the one thing you need to know about matrices is that they are operators, okay? Especially if it's a square matrix. A square matrix is an operator that acts on a vector space. In a vector space, you have a vector. Let's take a simple example of a two-dimensional vector space, x and y, and you have a vector, let's call that vector v. If I multiply this vector by a matrix, so if I take some arbitrary matrix, A, B, C, D, let's say, and let's say this vector has got x and y components. I'll call the x component v1 and the y component v2. Then this is going to give me a new vector, and the new vector is given by av1 plus bv2 and cv1 plus dv2. So that's the new vector. The x component of the new vector is a times the x component of the old vector, one of the old vectors, plus the y component, b times the y component of that vector, and so on. So this is a new vector. Now in general, this vector can be a very complicated thing. So the general shape of this new vector can be that it was rotated and it was stretched by some amount, because this can be anything. However, if ABCD is an orthogonal matrix, then the only interpretation for what this multiplication of the matrix does to the vector is that it rotates the vector by some angle. So that's why orthogonal matrices are very important. They do not mess with the length of the vector. So a matrix is said to be orthogonal, denoted by O. Don't confuse this with 0. If O transpose is the same as O inverse. Now remember the inverse of a matrix, which I dealt with in some earlier videos. The inverse is a complicated thing. You take the cofactor matrix and take its transpose, and that's the inverse, and divide by the determinant. So it's a very complicated thing. So you can find the inverse of a orthogonal matrix by simply switching its rows and columns. How nifty. You don't have to go through that elaborate process to find the inverse. And the other thing about the orthogonal matrix is that if you take an orthogonal matrix and multiply it by its transpose, it's like doing nothing. And that follows directly from the fact that O times O inverse is just the identity. That's the very definition of an inverse, is it undoes whatever the matrix initially does. So that's another interesting notion. Let me give you an example of a rotation matrix. For this two-dimensional case, a rotation matrix would be cosine theta, sine theta, minus sine theta, cosine theta. And the inverse, which is basically just the transpose, is going to be cosine theta, sine theta, minus sine theta, cosine theta, where I've interchanged the columns and the rows. So that clearly is a rotation by angle theta. Now if I change theta to minus theta, cosine does not get affected because it's an even function. Sine does get affected. Sine of minus theta becomes minus sine theta. So that's simply a rotation by angle minus theta. So this anti-rotation, if you will, undoes the effect of the rotation matrix. Then there is in the notes to this week, I also talk about some properties of the orthogonal set of orthogonal matrices, and you can look there. It's a fascinating structure known as the group structure. So the other type of matrices which are especially useful in higher physics like quantum mechanics and quantum field theory is unitary matrices. A unitary matrix is a complex matrix. So all the entries are complex numbers. And so I'm going to define a quantity called U dagger. So U with a dagger shaped object. And this is equal to the transpose of U times and the complex conjugate of each element. So for example, let's consider a matrix I 1 minus I. Okay, I'm just making up a matrix. That would be an example of U. So U dagger, well, what do I do first? I can do either one first, but let me first take the row and the columns and interchange them. So that's going to be I 1 minus I, and then I take a complex conjugate. The complex conjugate of I is just minus I, and the complex conjugate of minus I is just plus I. So that's the answer. So unitary matrices have the property that U dagger is equal to U inverse. So they are like rotations except in complex space. Here in orthogonal matrices are rotation operators in real space, whereas unitary matrices are rotational operators in a space of dimension twice the real space or complex space. So this is sometimes useful because a group of rotations, there's actually a class of rotations that's called the orthogonal group. In n dimensions, it will be called On. The symmetric group in n dimensions is called Sn. The unitary group in n dimensions is called Un, which means that it's going to act on n-dimensional complex vectors here, n-dimensional real vectors here, and n-dimensional real vectors there. So there is actually an interesting relationship between orthogonal and unitary, which we'll study later when we go to group theory.